I can introduce myself. Don't worry.
Pardon?
I can introduce myself.
Okay. So I'm going to stop.
Thank you, Diego.
I'm going to stop the share of my screen. We are going to spotlight all the participants or panelists, so you can see all the time the panelists.
Vale. So thank you, Leo and Gerardo, and everybody. Welcome to the Longevity of Numerical Tools, looking for the future of numerical simulations in high energy astrophysics. I'm Diego López Cámara, a researcher at the Instituto de Astronomía in Mexico City, at UNAM. And so today, Agnieszka Janiuk, Davide Lazzati, Fabio De Colle, and Jose Antonio De Diego will have this panel discussion. So it's going to be 3 questions that each panelist will respond. You will have 5 minutes. And after each question, there will be 5 extra minutes for you to interact with each other. If you want to add something, if you don't agree with something, that would be a lot of fun. So before we start the questions for all the people, I will present Agnieszka, Davide, Fabio, and Jose Antonio. So Agnieszka Janiuk is an astrophysicist working at the Center for Theoretical Physics in Warsaw, Poland. Her research primarily focuses on high-energy astrophysics, particularly in the physics of compact objects, as well as accretion disks, the launching of relativistic jets, X-ray emission, and nucleosynthesis. Welcome, Agnieszka. Davide Lazzati is an astrophysicist working at the Department of Physics at Oregon State University. His contributions to high-energy astrophysics are known particularly in studying GRBs and their associated phenomena. Some of his main contributions include analytical and numerical models that have contributed to the understanding of jet dynamics and its prompt emission and multi-messenger astronomy. Welcome, Davide.
Good morning or afternoon, everyone. It's a pleasure to be here.
Fabio De Colle is an astrophysicist working at the Instituto de Ciencias Nucleares at UNAM in Mexico City, known for his research in computational astrophysics, particularly focusing on the understanding of various astrophysical phenomena through numerical simulations. His work often involves studying the dynamics and radiation associated with cosmic objects such as supernova, GRBs, and the formation of stars. Welcome, Fabio.
Hi, everybody. Thanks for the nice introduction, Diego.
And then finally, Jose Antonio De Diego Onsurbe is an astrophysicist working at the Instituto de Astronomía in Mexico City at UNAM. His research involves developing statistical methods to detect variability in AGNs, gravitational lenses, and the solar system. Currently, he is applying neural networks to classify the morphology and estimate the redshift of galaxies. Welcome, Jose Antonio.
Thank you, Diego.
Vale, so let me just say, so in this first round, Agnieszka is going to begin, then Davide, then Fabio, and finally Jose Antonio. And so the question, a bit long, but so it says, numerical simulations such as MHD, GRMHD, RMHD, and RHD play an important role in the understanding of transient events. However, there are still open questions, unfortunately, that need to be addressed. These unanswered questions present research opportunities for the near future. Therefore, employing numerical of transient astronomy. And so just before Agnieszka begins, I will let you know when you have 1 minute left so that we keep time. And so you have 5 minutes, Agnieszka.
Okay, so yeah, thank you. It's hard to be the first speaker, of course. I'm very happy to be here, and thank you for invitation. And well, my research is, as you say, is focusing on the transient phenomena and high energy astrophysics. I study the jets, outflows, also the instability cycles in accretion disks, and all of these phenomena originate in the strong gravity environment and also in the environment of highly magnetized plasmas. And the ideal method to describe the physics there is run a serious numerical simulation. One of the aspects of some systems are also related with microphysics, the equations of state of dense matter. So it is another challenge to cover a very large span of scales, physical scales, from micro scales up to the parsec scales in jets, and micro scales in the accretion disk and base of the jet and the dense plasma. So it is very difficult task numerically. But I would say that the key question is the relation of process around the compact star with the radiation output, because what we see from the instruments that are used by astronomers is the radiation output. Yes, it is not this accretion disk itself, unfortunately. So we have the classical picture, which is an optically thick, geometrically thin accretion disk of Shakura and Sunyaev. And it is still used by people who are observers. They observe black hole and neutron star X-ray binaries. They observe active galactic nuclei, and they always fit their spectral energy distributions with some disk model, disk black body, or at most some non-thermal tail to the energy spectrum. However, this standard accretion disk is not the model that we want to run in our simulations. So the current state-of-the-art simulations have to face the problem of reproducing observables. Basically, they would have to reproduce the broadband spectral energy distributions and the long-term variability light curves. And it is a big challenge to model this consistently via the radiation MHD simulation. If we want to cover sufficiently long time scales, such as the viscous time scales, it is still not possible with 3D MHD simulation. They are limited to dynamical time scale at most. And we cannot describe long activity cycles of the accretion flow. As for the spectral energy distributions, it is also a challenge, because the physically motivated scenario follows from the ADAF principle of the two-temperature plasma, where the electron and ion temperatures are needed to follow from physical principles, and electron heating mechanisms need to be described. In the numerical simulations, this is done by some phenomenological or some ad hoc prescriptions at the moment. So it is a challenge to reproduce also the broadband spectral energy distributions. And still there is a problem to relate the jet and disk together. Widely used phenomenology is proposed by people who like to play with cartoon pictures rather than with physically motivated scenarios. So for me, the big picture needs to always be related with what people observe, and our theory and numerical models need to reproduce the reality. That's all.
We'd love for the reality to reproduce our numerical models, but unfortunately it's the other way around.
Yeah.
Okay, so Davide, what do you have to say?
Yeah, so I was gonna do a long speech about the importance of observation, but Agnieszka took that from me, and so it's gonna be worse for Fabio and Jose Antonio, because I'm gonna certainly say something they're planning to say. So I certainly agree that one of the challenges and promises of the last few years have been to produce observations from the simulations, and not just pretty artist impressions and images and animations that are very detached from what an observer sees. I think another aspect that we've just started to scratch is connecting the various scales. If we think about gamma ray bursts, for example, a lot of times the whole picture is simulated in pieces. There is the stellar evolution that leads to a progenitor that is simulated with one piece of software, and then that is taken and input into something that simulates the collapse and perhaps the formation of an accretion disk and perhaps the energy extraction from the central engine, which itself requires its own postulates like a density floor for black hole mechanisms or some pre-existing magnetic field, because the resolution of the simulations is not enough to really resolve the magnetic rotation instability. And then many times the jet is ejected and the simulation is stopped and is now taken into a different piece of software that simulates the large-scale expansion of the jet and perhaps the radiation of the gamma ray phase. And then this is also excised and put into a different piece of software that computes the afterglow. So 5 different steps for the same phenomenon, and each time a simulation is stopped and the result into a new software, something is lost and some new assumptions are made. So one of the hopes is that we can start to connect at least a few of these pieces together in the near future, and hopefully get a light curve or a spectrum that we can directly compare to observations. Here's the challenge I wanted to bring up, which is kind of what do we want our simulation to reproduce? In all kind of transients, it's kind of if you've seen one, you've seen one. Like all gamma ray bursts are different from each other. All supernovae have some different nuance. And so if we are hoping to have a numerical simulation that reproduces the exact observation of one event, it's going to be a hopeless case. It's going to be extremely challenging. On the other hand, if we hope our simulations are going to be able to reproduce kind of a vanilla average gamma ray burst or supernova or fast optical transient or radio flare, we're probably missing a lot of the important details. And I don't have an answer. I just have a question here and a challenge. What is the Goldilocks here? How much detail do we want our numerical simulation to reproduce without getting lost into the peculiarities of one particular event that might take a really long time to reproduce, and we learn very little because we just learn a certain particular that is not really fundamental to the phenomenon. So I think, and perhaps that maybe kind of already anticipating the upcoming question, that's a place where artificial intelligence and a development in that direction can help guide our future attempts and future numerical efforts. I'll stop here.
Okay. Want to rule them all, Davide, and then let's focus on the exotic ones. That's what's been happening. Okay, so sorry, Fabio.
Yeah, so first of all, let me thank the organizers, because this is a very nice discussion. And also what I have learned so far is that we have exactly the same idea about the same answer to this question. So actually I have prepared a few slides if the other speakers will not kill me before, because I do that, and the organizers allow me to share my screen. Let me show you. Yeah. Just to help me a little bit with this discussion. But you will see that what I will say, actually, it's very similar to what Agnieszka and Davide just discussed. So there are 2 approaches, basically, to study astrophysical phenomena. The first one, which was nearly the only approach until a few years ago, is to study idealized problems. So we take our cow and we approximate the cow as spherical uniform density ignore the effects of gravity in vacuum. And here I put an example. No, for instance, some simulations I did like in 2005, 2006, studying the how the magnetic field affects the propagation of a non-relativistic jet associated to Herbig arrow flow. So just studying a very idealized problem. No? So this is the first kind of problems we try to study in numerical simulations. And there are a lot of open problems which can actually be studied by using this approach. No? For instance, GRB physics is not clear and understood. No? The formation of the gamma ray in particular is still kind of a mystery. Supernova explosions mechanisms is something that it's really evolving mainly, if not only, by numerical simulations, idealized numerical simulations. Well, less and less idealized, actually, as a function of time. It's becoming increasingly clear that there is a variety of phenomena related with central engines, from relativistic supernovae to F-bots to superluminous supernovae and so on, low luminosity GRBs and so on. And it's not clear how this relation, what is the exact relation between this phenomenon and the central engine. Neutron-star merger, this was discussed by Agnieszka, especially the dependence on the question of state. The TDEs and the ubiquities of jets in TDEs, and so on. There are a huge number of problems which can actually be studied mainly by idealized numerical simulation, just focusing on one particular aspect of the phenomenon, no? Without taking in account all the details, as Davide said, the details which are proper of just a few or one single observation. The challenges with this are mainly that the computational demands are huge. We are going to 3D simulations, which include more and more physics. So in addition to hydro, MHT, if we want to simulate, for instance, the formation of the jet, we need to include the MHT, neutrino transport, if we want to do it properly, general relativity, and so on. So we need also high resolution simulations to properly simulate the turbulence. Well, not properly, but approximately simulate the turbulence. And well, the problem here is that our resources are limited, especially in Mexico. So especially if you hear from Mexico. So for instance, the most, just to give you an idea, the most powerful, the top computer in the world currently has 8 million of cores. And the most powerful computer in Mexico has 5,000 cores available. So just to give a scaling of how the resources are in Mexico with respect to other places. No? The other approach, which was mentioned by Davide, discussed a little bit by Davide in detail, is to study realistic problems. So to compare with observations. Also Agnieszka I was mentioning it. No? And yeah, here I put an example, which actually at that moment when I try to simulate this supernova 2009 BB, so you see the dots here are the observations, and the curves, the areas are the models, the result of a single model, comparing just doing a single simulation, and after that comparing the result of that simulation with observations. I was very happy of the kind of coincidence between the agreement between the observations and the models. But if you actually look to it in detail, you will see that the agreement is not very good, no? Because you see, for instance, the slope of these curves is much steeper than the model, and there are much more fluctuations in the observations than in the model, and so on. So there is a physics which is really not included in our model, no, which is actually present in observations. So we need to recognize that astrophysical systems are much more complex than what we try to simulate. We try to simulate spherical chaos, but actually astrophysical systems are more complex. And one important point, this was mentioned by Davide, is that we need to develop methods to compare simulations with real-world methods, strategies, whatever, to compare simulations with real-world observations. And I will tell you a little bit about one possible method as an answer to the following question. And I think it's already 5 minutes, no, Diego?
Yep. Thank you,
Thank
Fabio.
you.
And finally, Jose Antonio.
Okay, thank you. Okay, about opportunities, I think that one of the important opportunities is of predictive modeling. I mean, using computational resources and new algorithms, we can go to a very realistic simulations, and so we can make predictions and even help to make new observations. Another opportunity for students and so on is this of multi-messenger astronomy. I mean, astronomy has been limited by electromagnetic waves, but no more. And we have now gravitational waves and neutrino. See, if we can merge all these messengers of the universe, we can learn more. We can have an insight in the process of high energy objects. And the other opportunity is in parameter space exploration. I mean, we have several problems which are quite difficult to simulate or to treat, such as magnetic fields, this matter equation of states, jet dynamics. So these are opportunities to grow for a student. There are also challenges. I mean, just to include equations of general relativity, magnetohydrodynamics, and so on, are very complex computationally. We have also this how to present 3D and time scales simulations, treat the boundary and initial conditions of the simulations. We have also this problem with modeling accuracy. There are several problems that we can address, but are difficult, such as magnetic reconnection, turbulence, radiation transport. And finally, another challenge is how do we assimilate the data? I mean, how do we join observations and simulations? What are the trends in this subject? Well, I think that one important trend is to have the artificial intelligence integration into the simulations. I mean, artificial intelligence may optimize the simulating parameters, analyze the outcomes, and generate initial conditions. This automatically by AI. The other trend is to go to high performance computing. I mean, we can see that there will be a next generation of computers that will be in some time quantum computers and exascale capabilities. And the other trend is the collaborative frameworks. We have to, this is a new era, and the astronomers are not so isolated as we used to be. And this collaborative is interdisciplinary. I mean, it's not only astrophysics, it's computational physics, it's also data science. There are also collaborative platforms and open source software that we can use and we should use. And what are the skills that we need for
1
this?
minute.
Yeah, thank you. Well, I think that proficiency in computational methods, artificial intelligence and machine learning knowledge, that data science and software development. So I will finish here. To stay in this time.
Thank you. Gracias, José Antonio.
Okay.
So we have a few minutes if anyone wants to add something, if they want to say something that I didn't agree or something that you forgot. If not, I have a few questions which we can see if you want to.
Well, I would add one thing. Of course, I agree with all of you. In general, we all agree about the challenges of simulations, but actually what Fabio mentioned is also this computational power, which is not always sufficient for our needs, but of course, it is never-ending process that we want to have better resources because we build better models and so on. So the code optimization is one thing. The other thing is access to resources. The biggest computer we have access to from Poland at the moment is the European supercomputer located in Finland. It is 380 petaflops, as I remember. It is equivalent to 1.5 million of laptops. They advertise this. If you want, I give you in the chat box the link to the device website.
Can
But
we
anyway,
use it from outside Europe?
well, you can see. I'm not sure. It is a European resource. But what is important, and I want to highlight, is also the energy and the power for this machine is pure hydroelectric power. And it is currently very important to use the resources which are saving us from the energy crisis problem. So yeah, I'm not sure how it is on the other side of Atlantic, if it is a challenge or not to build such machines, or it is important for your governments, but in Europe it is. And that's why this machine has been advertised also in this way here.
I was going to ask what your feeling of GPUs is. Like, do you think the future is going that way or not?
I think, yeah, it is definitely. It is a challenge for programmers to rebuild their codes. Yeah.
If I can comment on that, the problem with GPUs is that the current models, I mean, the current methods to integrate equations are built with the idea of being used by CPUs. So when we apply those methods, the codes built for CPUs to GPUs, they are typically not very efficient. So what people say, I mean, people in the fluid dynamic community and so on, is that really we need to build, to develop specific methods for GPUs in such a way that they will be very, very efficient on GPUs. It's a completely different approach, no? But yeah, GPUs are not very used in astrophysics currently.
Yeah, I think the other issue with GPUs is that codes is not as portable as CPUs. It's very vendor dependent, and so that's a big drag on investing significant amount of time into converting a code in an efficient way, and then it has to run on a certain machine. So hopefully that the industry will provide an evolution like for CPUs, where you have compilers that make the code really portable.
Okay. And what do you think of code sharing, like making one big code instead of each one having your own code?
That's for the next question.
Okay, I'll leave it for the next one. So let's go to the second question. And so here, the question is, young career scientists interested in numerical simulations work within an environment of rapid and constant evolution. The integration of new technologies such as artificial intelligence, data science presents significant challenges. These challenges demand technical and specialized skills and an understanding of new algorithms and the ability to adapt quickly to change. Consequently, what challenges do future researchers face in the developing of numerical simulations and coupling them with new technologies? And so now it's going to be Jose Antonio, Agnieszka, Davide, and then Fabio. So it's all yours, Jose Antonio.
Thank you. Well, these challenges, I see a forcible evolution, which is basically we're searching for increased realism, complexity, and computational demands in these simulations. So the emerging simulations, AI, and data science will become an automatic simulation analysis. We provide simulations parameter optimization and simulations designed based on observational data. How do we integrate these simulations with AI and data science? Well, simulations and AI and data science may help to patterns to recognize pattern identifications and correlations in the data. Deep learning emulation of simulations, and also parameter space exploration. I mean, there are techniques such as adaptive mesh refinement and so on that may help to search for a better parameter estimates. And finally, what's the skills? I think what are skills? I think that an EU student needs to be a proficiency in computational methods. I mean, numerical simulations, computational physics, also in AI and machine learning in general, neural networks architectures, reinforcement learning, and supervised and unsupervised machine learning. Also in data science, of course, visualization, statistical analysis, and data manipulation. And finally, in software development, I mean, students need to know Python, of course, C++, probably even Fortran. And I think these are the challenges that students will face. Thank you.
Thank you, Jose Antonio. But so do you have like any courses that you recommend? Because that doesn't, like what you said, is not very astrophysical, very much physics, right? Like so.
It's general because, well, I don't work in simulations of high energy, so I can't provide an insight in this. But this is general, you know. I think that even if you dedicate, I don't know, to economy, you need these tools, and you need to use them.
But do you recommend like Coursera, or where can students?
For students, yes, well, you have Coursera is okay thing, and you have a lot of communities that you can ask for software or for anything. I think this is the future. I don't know.
Okay.
I am too old now for this future, but I foresee that it will develop like this.
Okay. Thank you, Jose Antonio. So now Agnieszka.
Yeah, so my comment is completely different, but I think just because Jose Antonio seems to be an expert in this artificial intelligence, and I am not, completely not, and I don't work with machine learning. I never tried that, and I think it's something that I need to learn, but I'm afraid of. So the point I would like to make is that all scientists, not only young scientists, but everybody must somehow face this challenge and get to use the artificial intelligence methods in everyday tasks, whatever they do, and try to familiarize with it and learn and understand. But also what I heard from somebody recently is that artificial intelligence is neither artificial nor intelligence, because it was made by human and it was trained by humans, so it can also make errors, a lot of them, and we are other humans who have to test and verify whatever this thing produced, if it is true and reliable or not. So I think essential thing is to be able to plan some basic tests and verify in the end if the results produced by artificial intelligence are robust or not. So for instance, I guess that it can produce a piece of code in Fortran, whatever language, but it needs to be verified by a human programmer, experienced person who would understand why the results are like that, and if this is not a bullshit completely, if this is something meaningful. it needs a human verification. That's my point. And from a scientist's point of view, another thing that maybe artificial intelligence can be useful for us, as for people who are writing texts. Yes, we are writing a lot of papers, and these papers are linguistic thing as well. Yeah, they are not only presenting numerical code, but they are also sometimes even a poetry. So I think that artificial intelligence can be somehow helpful for us to help standardize the language we use, so that we understand each other better. Not everybody is a native speaker in English. That's a problem sometimes for me. But I would like to be able also to verify somehow independently the content of the research papers, the methods used, or the literature which is cited by various authors. Sometimes I don't know completely what are the background papers. People cite their own works or the other groups' works, and you need to dig deeply into this literature. Maybe this could be done by artificial intelligence, but again, discuss it in the panel by experts, and then we can see if this artificial intelligence made a good choice of literature for us or not.
So would you recommend students to double check their sentences and paragraphs using some artificial intelligence platform?
Yeah, I think, yeah, that's a good thing to give to students, but of course with consciousness, yeah, and criticism. Yeah.
Okay. Davide.
Yeah, so I'm going to take a little bit of a different angle here, and so I focused on what is the best way to prepare for a young scientist, more in terms of what it would be like 20 years from now. And so I'm going to make a parallel. If you think about observations, right, there's people who build telescopes. Now there's people who operate telescopes, and a completely different set of people who ask for time on the telescopes and analyze the data. And the world of computational astronomy is very different, because there's the same person most of the time who writes the code, runs the code, and interprets the outcome of the code. And so we're kind of try to do many things, and neither of them we are complete experts of. And so the question is it going to remain like this, or are we, as a community, are we going to evolve to more specialization? I think people around my age, I am 50, I've been in research for 25 years, we never had a really formal education in how to code. We kind of learned it as needed. And it's an ongoing joke that astronomical codes are badly written codes, but if you ask a professional programmer to do the coding for you, then the code doesn't do what you need, and so there's a problem there. But maybe that's not how it's going to stay, and we already see some evolution with community efforts like the Einstein toolkit, and even earlier, like the Flash code was kind of a game changer, and now everybody thinks it's obsolete. But if you go back 20 years, it was the first attempt to create a general purpose code where the user didn't have to have any clue of what's under the hood. And so with artificial intelligence and GPU coding, we might be heading in that direction, where there's going to be a set of specialized scientists who are leading more in the computer science part of the world, and they will design the codes and write the codes, and then users who don't need to know what's under the hood, and they use things, and they might have artificial intelligence enhanced capability and so I think that for a young scientist, I think my recommendation would probably be, what do you want to be? In which of these fields do you want to be? Somebody with a big GitHub presence who does code development, or do you want to be more a user of a code? And so do you want to be on top of the newest AI algorithms and how to make things efficient and write new algorithms, like Fabio was saying before, that are optimized for GPUs instead of CPUs? Or do you want to focus more on the science? Because probably having your feet in both worlds is going to become more and more challenging. I mean, that's how things tend to evolve always. When things are new, everybody is a little bit of a master of many tools, but then specialization comes in.
1 minute.
Yeah, and so I think that's I don't think we're gonna get to the point like telescopes where you don't even run the code. You send an email to somebody, hey, run this code for me. Probably that's too much, right? So at least knowing how to compile and run and execute and restart the code, all those are gonna be, set up your initial conditions. Those are still gonna be skills that you need. But the coding itself, my personal guess is that is going to become a really specialized skill, and that is it's either your job to stay on top of that, or maybe it's not that important because you're not going to be doing that much coding anymore.
Well, I remember they asked me like 20 years ago, do you want to be a code developer or a code user? I said, I don't know. And I still don't.
Well, you're about my age. So.
Anyway, so Fabio.
Yeah, so first of all, let me comment about what Agnieszka said. So I strongly recommend to use ChatGPT for English editing, because ChatGPT really was a game changer for to drop the gap between English native speakers and non-English native speakers. So what I usually do, I write a paragraph, and after that I put in ChatGPT saying, check the English. I put the paragraph, and usually ChatGPT say that the paragraph looks good, whatever. I have just these minor suggestions. So I check the differences between the two paragraphs. If I like, I change the single words, the ChatGPT. Also, it's a way to learn English, to improve your English. So it's really strongly recommended.
Sorry,
Thanks,
I have to ask. But wouldn't the journals say, oh, this is artificial intelligence written and not?
No, so the point is that you need to write the text by yourself. So if you say to the ChatGPT, write me an introduction of long GRBs, and the ChatGPT gives you 5 paragraphs, that's not correct, no. But if you write by yourself the paragraphs, usually ChatGPT is a very gentle artificial intelligence system, which really doesn't change a lot of what you write. So it doesn't say, no, all your paragraphs are wrong, so you need to change everything. No, typically, no, just a few words, no, here and there, and you improve very quickly your grammar. So that's a recommendation. And yeah, again, I have a few slides about this. So about the traditional way to do numerical simulation, my recommendation for young researchers is that, well, we need to do more and more radiation. So I was myself dedicating most of the time to the hydro part, but I feel that nowadays the radiation is much more important. And actually, it's much more difficult to treat the radiation than the hydro. So, and I put here the car movie because really the kind of techniques, these ray tracing techniques used to make these movies are very similar to what we use in astrophysics, but okay. I was yesterday looking to compare, to have an idea how is going the field of numerical simulations versus the field of machine learning. So I was checking in the ADS, the abstracts containing the word numerical simulations. So you see here the evolution. Actually, the first paper with the words numerical simulation is from 1962. It was a paper on turbulence in stars. And you see that there is a rapid increase. Well, there is an increase, steady increase, until a couple of years ago. So you see here the drop in the last few years, which kind of I suspected, because I have the impression that less and less people are using numerical simulations actually, and more people are using machine learning. So if you compare, if you do the same, job for machine learning, that's what you get. So actually the first paper on machine learning was in the 19th century, like 1898, something like that, containing the word machine learning in the abstract. And there is a huge increase in the machine learning techniques, in the use of machine learning techniques during the last few years. So I guess the drop in numerical simulations is due to the fact that a fraction of people working on numerical simulations are now working on machine learning. No, that's my. So it will be interesting to see what happens in the next few years, if this is just a fluctuation or if this is really a steady decrease in the number of people working on numerical simulations. And I guess that it will be a decrease in people working on numerical simulation, because with the next year there will be the beginning of the observations by LSST and other surveys. And in the next few years, there will be more and more surveys with a huge amount of data available to analyze. And that will shift necessarily the research towards the world of machine learning instead of numerical simulation, which in some way it's a pity, because that also means that there will be less deep studies to understand the physical phenomena, and more like statistical analysis and so on. Okay, so the challenges for, this was already mentioned also by the other speakers, the challenges for young researchers are, in my opinion, that they learn to, it's much more difficult with respect to what were the challenges for us, because they need to learn about numerical simulation technique, but they also need to be proficient in machine learning, artificial intelligence, data science, and these kind of things in the next 20 years. And my suggestion is that, and my idea is that also people will need to learn about adaptive techniques and machine learning applied to numerical simulations. And nothing. That's all for me. Thank you.
Okay, thank you. It would be interesting in your plots if you could put like a age, if the young researchers are the ones that
you
are
can't
doing,
you don't get that from ABS.
Yeah.
But let me comment something if I have time. Do I have time?
Yes, you have a minute and a half.
So with respect to what Davide said, because yeah, I agree that it's becoming increasingly more and more difficult to do everything by yourself, no? And with the interaction between numerical simulations and machine learning, artificial intelligence techniques will become more and more difficult. Yeah, so probably we will need to be part of large groups, or there will be large groups developing the software. The risk of that is that we will use, people will use numerical simulations of black boxes, which is very risky. But yeah, I think it's the way how it's going.
Okay, so with this, we can actually open discussion between you if you want to add or say something else.
Yeah.
May I add something? Oh, okay.
Okay, let's start
wait.
Agnieszka and then Jose Antonio.
So if you allow me to share screen, I want to share one slide, actually, because I don't know how to describe it. Can I?
Yeah.
Yeah, okay.
I didn't have any problem, so yeah.
Do you see this?
Yeah.
This slide now? There is the scientific universe. It is a slide which I showed to students on my last lecture. And you see, this is made by artificial intelligence, taking the data from archive, where these points are representing the papers in specific branches of the archive. And the astrophysics is there on the top right corner, the computer science in the bottom left corner. It means that papers do not cite each other's from these two islands on the scientific universe. So question by Davide, I think, that want to be a programmer, or do you want to be a high energy astrophysicist?
Wait, we're losing you a bit, Agnieszka. Or is it me?
No, I think that
it's
we
Agnieszka.
are listening.
So let's, while Agnieszka reconnects, do you want to comment something, Jose Antonio?
Yeah. Well, that's now a confusion between ChatGPT, for example, and what machine learning is, I think. I mean, the ChatGPT is a large language model, and it's very good to say, for example, make me the framework for a paper. For example, you can do that. You can also use it for computing code. But it's not only this kind of things that you can do. And probably large language models will evolve to a specialized tasks, such as, for example, lawyers or writers or whatever. But this world of the machine learning and neural networks in particular is much broader and much interesting. For example, we can have these pins, physically informed neural networks, that you can put physics into the neural network loss function, and so you can model very well with a neural network, but using physics. And I don't know if you have heard about the GANs, generative adversarial neural networks. They are used for images, for example, to produce a person and then put a bird or whatever. But I can see, for example, one use, which is not exactly a GAN, but it's similar, that you use a simulation and real data and put it for a neural, introduce them to a neural network, and it will say, this is real data, or this is a simulation. And so you can fine-tune your simulation that it's impossible for a neural network, at least, to distinguish from a real data. So we have a lot of opportunities here to work with these two techniques altogether.
Yeah, well, that's risky also, that you won't be able to distinguish between something which is computer generated from what is real observational data. Anyway, so finally, Davide, do you want to add?
Yeah, I want to comment on a couple of things. The first one is the ChatGPT. There is some discussion going on here in the US, especially funding agencies like NSF, into creating a system for acknowledging the use of generative AI in like proposal and paper writing. So it's kind of recognized as a tool. And so I think some NSF programs are experimenting with, writing a section to say, I use ChatGPT for spell checking or for improving my English, or so that is out in the open. It's certainly not something that is demonized. And as an also non-native speaker, I do use ChatGPT a lot for improving my English. And the other thing I wanted to comment on what Fabio was saying about we're going to be flooded by data in the next few years. And to me, it's unclear what that's going to do to the field, especially to is the theoretical interpretation community going to grow proportionally? I don't think it's possible. There's just not enough people in the world to grow the interpretation at the same pace the data collection is going to grow with this new survey telescopes and missions. Yeah, we might end up, and I think in the transient world, we're already seeing that there are just so many different transients that we're kind of lost. We're at a loss. What are we going to try to explain here? There's so many different things that it defies kind of our ability to classify things and decide what needs an explanation and what is just an artifact. Also, kind of going back to my first comments, where is the Goldilocks between diversity and trying to classify things into a comprehensible scheme or scenario?
Okay.
Again,
And
I have questions and challenges, but no answers here.
quick reply, Fabio. 1 minute.
Yeah, just a short comment on ChatGPT. So there is something funny happened to me when I was beginning to use ChatGPT, actually related with Diego and Davide, that I had an idea, scientific idea. So I write into ChatGPT. I asked to ChatGPT, what do you think about this? And ChatGPT said, oh, this is a very nice idea, whatever. And I said, do you know of any paper, existing paper, in which people have worked on that? And ChatGPT said, yes, there is this paper, Lazzati, Lopez Camara, and Astrophysical Journal, blah, 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 blah. And I was thinking, oh my God, I didn't know about this paper. I was checking and the paper was not existing.
Ah,
There was no any paper. So I was asking to ChatGPT, why are you lying? There is no this paper. And ChatGPT said, oh, I'm sorry. Yes, it was a misunderstanding. The correct paper is this one. Lazzati, Lopez Camara, whatever, with another reference, which was also a false reference. No, so ChatGPT for some reason makes up things.
Yeah.
So yeah, we need to be very
I
careful.
recommend Perplexity. That one gets right the references.
Okay.
So for future, ask Perplexity
Okay.
or ask Davide and me.
Yeah.
Okay, so let's jump to the last question. So in an era,
Jose Antonio wanted to comment something.
Sorry. No, it's true. ChatGPT hallucinates very well, but you have these GPTs and plugins in ChatGPT that you can use it. For example, Scholar IA, and there are several more, and they provide actual references. You can ask, for example, I want a reference about this, and it's probably not the reference that you want anyway, but it exists.
Okay, so let's use those plugins.
Yeah.
Oh, well. Okay, so let's go to the last question. So it says, in an era where artificial intelligence, data science, and related technologies are increasingly dominant, will numerical simulations become obsolete, which we've sort of talked about already, or the integration with new technologies, or will the integration with new technologies promise advances in the precision and efficiency of these simulations? So now we're gonna do Davide, then Fabio, then Jose Antonio, and finally Agnieszka. So go ahead, Davide.
Sorry, you caught me by surprise. I thought I was going to be among the last in this question.
I'm not the first, Diego, in this one?
Yeah, I think Fabio is the first.
Yeah,
You didn't touch the microphone.
it's Fabio, Jose Antonio, Agnieszka, and Davide. Diego, you are
No
mute.
tienes un micrófono, Diego.
Shoot, wow. Yes, I was looking at the remarks. So it's Fabio, Jose Antonio, Agnieszka, and then Davide.
Ah, yeah.
I was
you
jumping
wanted
to the end already.
you wanted to take me out the opportunity to be first.
Yeah, Fabio, Jose Antonio, Agnieszka, and Davide.
Yeah, so
Sorry,
this is a
Fabio.
difficult question because basically Leo and Gerardo want us to predict the future, no? So my first reaction to this question was, I will share again, was this, no? That the artificial intelligence is evolving so fast that it's very difficult to predict. So if you want to me to predict the future, I'm kind of a catastrophistic person. So learn from Sarah O'Connor and prepare yourself for the worst case scenario. No? Okay, but so I think the challenges were already discussed by us previously. No? So we need collaboration between experts in numerical simulations and experts in artificial intelligence. There is the risk of using the black box libraries. So libraries will be developed by a smaller number of people. And I mean, there will be a part of the community developing libraries and a part of the community using the libraries much more than now. And the other risk that I see is that it's becoming so rapid, the improvement in technology, that we can be very obsolete quickly. And let me put a few questions I was thinking about. So the first one is, researcher will be replaced by artificial intelligence. I think, I mean, I don't know the answer now, but my impression is that in 100 years, probably yes, no? Because, I mean, artificial intelligence will become more intelligent than what people are. But not, I will guess, not in a few tens of years. So for young researchers, this will not be a problem yet. And the second one, the coupling between machine learning, artificial intelligence, and numerical methods. So there are some techniques used nowadays. They don't work very well. For instance, instead of computing the fluxes using normal techniques, people compute the fluxes using machine learning. Because the problem in numerical simulations is that we use a big box, we compute the fluxes between different cells, for instance, when we solve the hydrodynamic equations. And we do again and again this calculation without taking into account the calculations previously done. No? So the idea in machine learning is that we should, if we have done already the calculation of a certain between two sets of values for density, pressure, and velocities, and we repeat the calculation for a similar set of values, we should already know the answer now without doing the calculation directly. So that's the idea of applying machine learning to numerical simulation. That's one way to applying machine learning to numerical simulations. Up to now, this, as far as I know, this does not work very well. It, in some cases, it has a small increase in velocity. It's used mainly in fluid dynamics. In astrophysics, it's not used at all. There are people in fluid dynamics trying to use these techniques, and they have small increases in velocity in the computation of the simulation. The other one is, yeah, for instance, let me comment about the last point. Learning systems, not only in a single simulation, but by coupling several simulations at once. For instance, we run sets of simulations. Davide does simulations, I do simulations, and my simulations do not take into account the simulations done by Davide. No? And again, we could use a system, a machine learning system, in which the system could learn from the simulation of Davide when doing my simulations. Okay, but again, this is not done yet. Probably this will be done in the future, no? But I'm not sure on which time scale. Thank you.
Okay, so Jose Antonio, please.
Okay, thank you. Well, when the IA makes these numerical simulations, I think one of the possibilities is when you have a very large database, and you can train very well the artificial intelligence, and you can get models with better inside the simulations, in the sense that it will look for things that you don't look in a simulation. Also, when, for example, in issues like optimization tasks and parameter space exploration, the artificial intelligence may be much better than simulations. But I don't think really that they are antagonist, simulations and artificial intelligence. I think that they will be integrated, simulations, data science, and artificial intelligence. And it will be used for enhancing the precision and efficiency algorithms, and refining the granularity of the simulations, for example. In automatic analysis of the results, such as pattern identifications in the results of the simulations, and checking for anomalies and correlations between different variables. The neural networks, for example, have the do not need that the relations are linear. They can find non-linear relations. It's very useful for detecting this kind of relation between variables. Also for automatic parameter adjustment, and I think one of the things that we need is these multidisciplinary approaches. No, I mean, astrophysics, applied mathematics, statistics, computer science, in particular computer physics. Some key points, maybe this enhancing the computational power. I mean, GPUs and TPUs will not have an important impact in this. It's data handling and processing, data storage, data transfer, advanced visualization. I mean, 3D, virtual reality, research, analysis. I mean, it will have an impact on research analysis, education, and outreach. And I foresee what will happen in some years. Probably I will be wrong, but in 5 years, I see that there will be a higher speed data transfer and artificial intelligence hardware accelerators. In 10 years, we will have a data transfer by 6G, for example, or something else. The quantum computing will be something usual. In 15 years, we'll have some holistic integration of artificial intelligence into research. Some things like automatic hypothesis generation, real data time interpretation, and there will be some quantum simulations now in 15 years. In 20 years, we have an advanced neural interface technologies. So artificial intelligence will be more confidable than it's now. And quantum computing will be a big choice.
We'll need to have this meeting in 20 years, Jose Antonio, to see if you got it right.
I'll be retired.
Okay, so Agnieszka, please.
Yeah, thank you. So first, let me apologize. I'm not sure when I missed part of the discussion because my internet is not good enough here actually for sharing my screen. So I will not try to do that again. I just want to get back to this idea, which I wanted to show you with an exemplary plot, but still the plot was about connection between computer science and astrophysics, which are somehow distant from each other, at least on the map of papers, research papers on these two fields that are published on arXiv. They are very distant from each other, and people from these fields, computer science and astrophysics, do not communicate. We attend, Gerardo will attend this week with me the conference of supercomputing, and we have very small separate session about applications and we are users of the supercomputer. We are not anybody that who would be important in this branch. Yeah, but I don't want to criticize these people. Still, they are researchers. However, there is a risk, quite a fear in the community of IT people who are working in business that very soon artificial intelligence will replace them and they will lose their jobs because artificial intelligence is supposed to do much quicker all the routine tasks, and humans will not be needed for that. I still hope the people who are researchers will be needed because we have human brains, and human brains are not so easy to be replaced in the end. I think as for the simulations which we are talking about, they are based on the laws of physics. And physics is something that human has to understand well. For hydrodynamics, we have to cope with nonlinear effects. So for instance, the parameter space to be probed is not equally spaced, not equally distributed. Sometimes very small change in the initial conditions will lead to enormous change in the result because we go into chaotic behaviors. This is something that we have to deal with very carefully, and I don't think artificial intelligence will replace every kind of parameter space probing that is of physical meaning in this field. It can help to optimize, to do the regular standard tasks more quickly. It can save us time with fitting the models to data, for instance, whenever it is easy, and routine work. I guess artificial intelligence is supposed to be very useful. And we can use it for saving our time, yeah, for better and more important work. That's my point. Yeah, I think that's all for now.
Okay, thank you, Agnieszka. And finally, Davide.
Yeah, so as the last contributor here, I just draw lines on things I wanted to say. I agree with everybody. The one last thing that was not mentioned, I think, is that AI development is now heavily led by the private sector. And maybe this is something that is very different from other things like hydrodynamic codes. There are private hydrodynamic codes, but they don't have the kind of physics we need. And so there's no interest from our community to look at what the private sector is doing in that. Right or wrong, maybe we should. But for AI, there is big economic driver for the development. And I think that's another variable that is very difficult to predict how it's going to affect science. Yeah, I think that what Agnieszka was pointing out is very little contact between us and the computer science community. And that is a weakness, is a big weakness. Why sometimes I feel we still do things like they were done 20 years ago. And we are still in the kind of mode, oh, if I have a problem, I'll figure out a way to solve it, rather than learning the tools. And probably because a lot of us self-taught these, and now we are teaching the young generation. And so maybe we should take stock of our own limitations and try to bridge this gap more. Otherwise, I feel we're going to be left behind because when the private sector sees an economic interest in something, it's just gonna take off. And so that I think something we should focus on, and it's probably early still, but even ChatGPT is at the end is just assembling known knowledge. It's not generating new knowledge really. And so we can kind of look at it and be a little snobbish and say, oh, but it doesn't have a brain, so I'm still gonna be needed. But there is this article that was published some time ago of the 10 most threatened professions by AI, and a university professor was one of them. Which might be good or bad. Maybe it's good because it means we don't have to teach anymore, and we're just going to dedicate all our time in research and at becoming good at writing code and running codes. And but maybe it's really that we are overestimating our uniqueness in this game, and a lot of what we do is going to be replaced by AI in 20 years. And so what part is irreplaceable that we should focus on making it our priority? I don't know.
Speaking of private companies, here in Mexico at UNAM, Amazon Web Service is actually offering now time for the high computational simulations. So it's something I never would have expected. AWS giving us time for hydrodynamical simulations, and Amazon is interested. So,
but it's more expensive. It will be much more expensive than buying a local supercomputer, no?
Yeah.
If a lot of people use it.
Yeah, but their service is quite efficient. So anyway, but then, I just have one question, David. So what do you recommend the students? So they need to know computing, but they also need to know astrophysics. So what would you recommend them to learn before, like computing and then focus on astro, or the other way around?
Good question. Probably a little both at the same time, but I think, as I was saying before, it's probably a decision to be made is what's everyone's priority. Do I want to be an astrophysicist who knows enough about computations that I can use a code without tripping at the first obstacle? Or do I want to be a code developer who knows enough about astronomy that they can write meaningful codes?
Okay. So we have a few minutes. Does anyone want to add or reply?
Can I comment on that?
Adelante.
So I agree that one should look to the job market, but my idea is that students should just do whatever they like most, no? Because if they are more interested in numerical simulation, they do numerical simulation. If they are more interested in data science, they do data science, without thinking what will happen in 10 years, because it's so difficult to predict what will really happen, no? That I don't know if it's worthwhile really to define your career based on your prediction of the future instead of what you like the most now, no?
Yeah, I think you are definitely right in this point, because the most important thing is our own motivation and passion for something. If you don't have passion for programming, you will not do this. If you don't have passion for astrophysics, you will not do this anyway. Yeah, on a good level. So, why to spend your time at all?
Also, if you are really passionate about programming, maybe programming, data science, and so on. There are so many job opportunities outside the academy that probably it's better if you go outside the academy, no? Instead of staying.
Yeah, of course, if you have passion about money, then better go somewhere where you can earn the money.
Yeah.
Well, I would say that a student now has to be prepared for everything. I mean, and it's not learning this and then forget it and pass to other things. You know? They will have to learn astrophysics, but they will have also to learn machine learning and simulations, and be actualized in every aspect. Otherwise, they will not have a great career in astrophysics. And well, I think that this is, for me, the most important thing. You know, that if you want to dedicate to astrophysics, you have to be prepared to make a lot of work all your life.
But then, just so that the students are not overwhelmed, the way I see it is 20 or 30 years ago, I didn't have like, I was only research. And if I didn't finish in research, my life would have collapsed. And now you have this other job opportunity in which you can have so many other professions, well-paid professions, which is good for the students. So I understand that research opportunities are getting broader and more difficult for students, but if they prepare themselves knowing astronomy and computer science, the job market will be so much bigger than what we had 20, 30 years ago.
But it's not a thing of astronomy only. I mean, in whichever career you're continuing, you have to be updated, and it will be more important in the future. It's not that I made my career on lawyer, as a lawyer, and I forget everything since then. No, you have to see very fast, and otherwise you will not be competitive. Not only in astronomy, in many fields.
I have a provocative question for the panel. What about quantum computing? Should we recommend students to look into quantum computing, or is it something 50 years away?
Are you asking me?
Jose Antonio said 20 years from now.
Yeah, I think that you have to be prepared for quantum computing, but you cannot dedicate your life now to quantum computing, because you will do nothing basically, unless you are working with quantum computing. I don't know. But otherwise, you have no job. No? But you have to be prepared. You have it's 5-10 years. This will change.
Okay. Anyone else want to add something about this last question? Okay, if not, then we move to our last segment, which is final remarks. If you want to address the students, or if you want to say something else, now is your opportunity. And so now I am getting the list right. So now it's Davide, then Fabio, then Jose Antonio, and finally Agnieszka. And here, 2 minutes, please. So go ahead, Davide.
Yeah, so I think the bottom line is predicting the future is very difficult always. And no, if I were a student now, when I say decide what you want to be and focus on that, I certainly not saying just look at the job market, or still follow your dreams. But as we say in Italy, cum grano salis. But I don't know how to translate it, but kind of use your brain and not just your emotions. AI is just starting and is very hard. I mean, I think we can predict some of the effects it's going to have, and it's going to influence the way we run numerical simulations. We certainly like to think that our brain still gives us a unique role, and researchers will be there 30 years from now. But flexibility, it's going to be and it's I realize I'm a little self-contradictory because I had the same from one side I say specialize in something, and then I'm going to say flexibility is going to be key. It's going to become more and more difficult to be the expert of the most important thing. If we look at the 20 years ago, there were the luminaries, there were the Martin Rees, the Roger Blanford. I mean, they're still alive, but no, they're towards retirement. And already we don't have an astronomer that does it all. We don't have the 40-year-old Martin Rees anymore, or Roger Blanford, or those kind of figures that kind of had the theory of all aspects of astrophysics in their head. So we're gonna get specialized. At the same time, things are changing at a pace that is increasing. And so balancing flexibility with specialization is going to be a very important aspect of science in the future, I think. It's not easy, but you're young and full of resources.
Thank you, Davide. Fabio?
Yeah, I don't know if it's because we are from the same city, but I always think something similar to what Davide just said. So yeah, when I started my PhD 20 years ago, I was beginning to work on numerical simulation, and thinking about the future, I was thinking, oh, okay, I will work during the next 20 years on numerical simulation. So it was much easier actually to somehow predict the future and predict the kind of changes would happen. Now it's much more complicated, no? There will be huge changes in astronomy in the next few years with this big data available, big amount of data available for everybody. And yeah, and also the machine learning, artificial intelligence. So everything is changing very, very fast. It's much more difficult to see what will happen in the future. And yeah, I agree with David that we need to adapt to the rapid changes. So I'm wondering that really Gerardo and Leo organized this discussion to kind of get answers about the future, and I just got questions and doubts. So I don't know. I think it was very interesting, no? But I don't know how happy will they be about this.
Maybe they're happy that they're not the only ones who are confused, but even you, the
Yeah.
panelists, are somewhat confused.
Yeah, yeah.
Okay, so Jose Antonio?
Okay, thank you. I think that we have seen that there are a lot of opportunities for research and your career as a young astronomer. I will not get deeper about flexibility and this kind of preparation for change that has been commented by David and Fabio. I will remark two things maybe, is that new technologies now are very important and will be advancing very fast. But you have to have a balance between what you're doing and what you can do. I mean, if you adopt new technologies immediately, maybe you are making a more precise research, but probably you will use much more time. So you have to have a balance between these things. And another thing that we have not commented here, but I think is very important, is about communication. You have to know how to communicate. And it's not only to speak foreign languages also, but it's also how do you write, how do you express. I mean, meetings will be held by virtual meetings or whatever, but you have to speak, and it's important that you know how to do it. So communications, I think, will open you many doors in research and outside of the academy. So do not forget this. Be prepared.
Thank you, Jose Antonio. And last but not least, Agnieszka.
Yeah, so my final remark is similar, that one needs to be prepared for a lot of changes and be flexible, because planning your own career is currently not possible. It was not possible when I was young and I started my career in science. I could not predict my future for more than 5 years ahead, and even now. And this is also what I'm telling not only to students, but to my own children. Especially my son is a student himself, and he's very well organized person, and he plays chess, and he wants to know always many steps ahead what he should do. And he keeps asking me what I would advise him for his career. And I always say, I cannot tell you, because I don't know the future. I'm not a fortune teller. And you have to be prepared for many opportunities, many changes, and also flexible. And also what is important maybe is some personal attitude, which makes you more trusting to other people, and be prepared for group work. This is difficult for us scientists sometimes, because many of us are introverted people, and we are hesitating to collaborate within a big group. We prefer to have our own tools and our own code and control everything. But now it is much more important to somehow go beyond this comfort zone and talk to other people and trust that their solutions are maybe good, and just take them. And somehow learn to find ourselves a pleasure to be in a group. Yeah, not always be the leader, not always be the loser, but be a member of the group and collaborate. Thanks.
Okay, thank you. So thank you, Jose Antonio, Davide, Fabio, Agnieszka. Thank you for this nice panel, round table, at least in Spanish. I don't know, Leo and Gerardo, do you want to add something?
Yeah, it was a pleasure to have you. And also, as part of this discussion panel, we have a certificate of participation signed by the director of here of the Astronomy Institute, and I will send you later at the finish of the discussion panel. But it was a really nice discussion. I think that, yeah, we have a lot of questions, Gerardo and I, but also somehow we have security in some stuff, like that the numerical simulations will be also a tool, but we need really learn how to manage different tools and how to adapt quickly to the changes that are coming in this near future. Gerardo?
Yes. Also, thank you very much to the panelists for accepting the invitation. It was very nice discussion, and I learned a lot. And so I was wondering if some of the public had a little question, some seconds to explain of that. Because I guess there is some young people that join us. But I don't know if someone has a question, but I have a, let me ask just a little question. You mentioned this new tool with GPUs. What specifically doesn't work with GPUs? Because I was wondering, for example, in the Riemann solvers, the typical methods to solve, is that the part that cannot adapt to the new techniques, or what methods?
Fabio,
But
Davide?
I
or
don't know if
Agnieszka?
someone knows better than me. Probably yes, because I'm not really an expert on GPUs. But the main problem is with the memory, no? That the memory in GPUs is more limited. So if your calculation that the GPU is doing goes above the amount of memory available, it begins to interchange information with the GPU, with the memory which is located, with the CPU memory, let's say, which is located far away from the GPU. So the calculation it's not any more efficient.
Okay.
But I don't know if someone is more expert than me, no, on this.
Oh, no.
Yeah, thank you.
And that's true, but there are lots of GPUs. You may have a chain of GPUs, so I don't know how this will affect if you have enough money to buy GPUs.
The other problem I'm aware of is that typical GPUs used for gaming are single precision. So they're not very good for numerical calculations. So people usually use specialized GPUs, which are much more expensive to do numerical calculations. So because, yeah, I was thinking I will buy a GPU with 5,000 cores. I will use it in my computer and I will get a 5,000 increase in speed, but it's not so easy, no? Because that GPU is not really built for our numerical simulation. That's why people are beginning to think, okay, but why we need to change the GPUs? We should change our numerical how our numerical simulations are done. No? So if you look, for instance, to YouTube videos, there are impressive fluid dynamic videos using GPUs with particle movements and these kind of things, which are really amazing. But those is not very easy to adapt those to astrophysical simulations because we have strong shocks. So.
Well, it depends. If you are working with images, you need the GPU, and even a non-mathematical GPU will help. If you work with tabulated data, sometimes it's better, sometimes it's not so much better. It's not clear.
Mhm.
Yeah, thank you.
Well, let's close the discussion. And so thank you once more to all the panelists, to Leo and Gerardo, for this the longevity of numerical tools, looking for the future of numerical simulations in high energy astrophysics. And so with this, we wrap it up and hopefully see you all in the near future.